In this video, we'll be talking about improper integrals. And for this, notice that we've had a definition of a proper integral, which is what we're used to. We're looking at a bounded area over a specific interval AB. Your limits of integration are finite. In other words, you're not approaching positive or negative infinity, and the function has only finitely many discontinuities over the interval. So we're going to have a couple of different types that we're going to look at. And for the first one, just to get an idea of what we're talking about, it's a good idea to draw a sketch of a given function. And for this function, notice we have 1 over x squared. And so if we draw this function, it's just like any other function that's 1 over x. It just kind of looks something like this and does continue on. And then notice they wanted us to look at this from x equals 1 to x equals t. And so here I'm going to look, let's draw our line here for 1. Let's say that's a good value, x equals 1. And then we're going to look at somewhere out here is a good value, x equals t. So I'm talking about this bounded region inside here. That's what we're looking at. And so when we do that here and we integrate, do keep in mind in our integration, we rewrite this as a good idea. So we're integrating from 1 to t of x to the negative 2 dx. And then we're going to look at our actual integration here. So that's going to be a negative x to a negative 1. And we're evaluating that from 1 to t. And so notice we're going to get a negative 1 over t minus a negative. So that's going to give us a positive 1 over 1, which is 1. So we see that when we integrate this, we've got something strange going on here. And look at part B. It says, what does this answer tell you about A at t? Well, as we plug in values for t, let's think about this. As we're plugging in these values for t, really this entire thing is getting smaller and smaller and smaller. So that term is getting smaller, which means that this whole idea, this bounded region, is probably going to have a value really close to 1. So for this, I'm going to say that the value of this is going to have to be close to 1. We can look even at the limit here. Notice in part C wants us to find the limit. So look at what we would do. We're going to have the limit as t approaches infinity of a at t, and keep in mind we found a at t to be negative 1 over t plus 1, and notice that limit would tend to be 1. Okay, so some helpful hints here that we have. For the first part, remember that you're really evaluating two different types of problems. You have an integral problem and a limit problem, and you do those separately. And then when you're breaking down the improper integral, you need to make sure it's only improper at one place. In other words, either your lower or upper endpoint has to be infinity. If it's both infinity, both the upper and lower, then we have case 3 that we would look at. All right, so for this one, notice that we do have an upper bound that is improper. So what we're going to do is kind of like a U substitution, and we're going to try to remove that infinity from the equation, so to speak, for just a little bit. So what I'm going to do here is say, well, this is the same idea as the limit, and most of the time you're going to see a b used there, but it doesn't have to be a b, just some letter there. As b approaches infinity, and now I'm going to have the integral from 1 to b of 1 over x dx. And what's going to happen is we are going to solve this portion And once we have that portion, then we're going to go back and do the limit part of that answer. So that's why it's talking about two problems in one. So let's go back and do our integral. So here, that portion there, if I integrate 1 over x, the derivative of the bottom is the top, so you know it's natural log. So our next step, we're going to have the limit as b approaches infinity of, and I know this whole portion here is going to be natural log, and I'm going to use some brackets to keep some stuff separated. Natural log absolute value of x, and I'm evaluating this from 1 to b. So now that's going to be the limit as b approaches infinity of, and this is going to be the natural log, absolute value of b, minus the natural log, absolute value of 1. Now on the inside here, notice you have the limit as b approaches infinity of the natural log of b. And notice minus natural log of 1, that's going to go out to 0. So notice what's happening here. I want the limit as b approaches infinity of the natural log of b. And if we think about the graph of natural log of b, it's going to continue doing something like this. So it's ever so slowly shooting off toward infinity. So notice that we have an improper integral. We've gone through all of our steps, and notice that my limit is going toward infinity. And so what we're going to say here is that this diverges. This is going to diverge. In other words, it's not approaching a finite value, a nice normal number. So here, that area is infinite. That's what we have found. And let's make ourselves a note of that. The area is infinite. We were not able to find a value for it. Okay, so after looking at that last example, this is getting us toward what we can call, we've got a theorem here, and we're tending toward our series a little bit more. And we're going to see that when we have our setup that we just looked at, that with this value p, all of that's going to be convergent when p is greater than 1 and divergent when p is less than or equal to 1. So that's, if we knew that, then back in that first example 2, we could have known right away that that was going to be divergent. All right, so let's look at example 3. This is going to be where our lower bound is improper. So we're going to start again with the limit. And I'm just going to choose t approaches infinity, negative infinity, of the integral from t to 0 of x times e to the x dx. And this looks like we're going to have our integration by parts. So over here to the side, we're going to let u be equal to x, du is dx, dv is e to the x dx, so v is going to be e to the x. And so now, if we look at this, we have our limit as t approaches negative infinity of, and I'm just going to put in these monster brackets here. We've got uv, so we've got our sunshine minus our voodoo, so the integral of v du. All right, so now let's look. We have our limit as t approaches negative infinity of, oh, and I need to put in my endpoint, sorry guys, from t to 0 up here. And I'm also evaluating this from t to 0. So now we're ready to go ahead. We have our x times e to the x evaluated from t to 0 minus the integral of e to the x is just e to the x, and that's evaluated from t to 0. Right, and continuing on, Let's see, I'm going to go ahead, bring down this limit again as t approaches negative infinity. And subbing in here our 0, well, we're going to have 0 times e to the 0 minus t times e raised to the t power. And then minus out here, we're going to have e to the 0 minus e raised to the t power. All right, so we have our limit as t approaches negative infinity of, that's going to go out to 0. So I have negative t e to the t minus 1 plus e to the t power. Okay, so now we're ready to go ahead and start subbing in some of this stuff to see what we're going to get. And let's see, we have here, I'm going to just plug in and say negative big. So this first part here, we have the negative, and then we have negative big, e raised to the negative big. So all of that's going to go out to 0, minus 1 plus e again to the negative big. Now, the reason why I say that's going to be 0, keep in mind that's going to be big over e raised to the big because we have that negative exponent. And so that's why that's going out to 0. Then you have minus 1 plus 1 over e to the really big again. So notice all of that, I end up with negative 1. So there we go. So we're going to say that here, notice we got a nice finite value, and so this was convergent. All right, let's look at our next example. And again, notice this one, we've got 2 places from negative infinity to infinity. So we're going to divide this up at some point along through here. Probably 0 is a good place to divide it up. So let's see, I need to separate this to be the integral from negative infinity up to 0, 1 over 1 plus x squared dx. dx, not dt, goodness. Plus the integral from 0 to infinity of 1 over 1 plus x squared dx. All right, so now we've got to look at doing some funky substitutions here. And a and b, sure, it looks good to me. So I'm going to say the limit as a approaches negative infinity of the integral from a to 0 of 1 over 1 plus x squared dx, plus, and then this one's going to say the limit as b approaches positive infinity of 0 to b of 1 over 1 plus x squared dx. All right, so that looks like if we integrate 1 over 1 plus x squared, that's going to be our inverse tangent. So we have the limit as a approaches negative infinity of arctan, or inverse tangent, however you want to write it, of, let's see, x, and I'm evaluating that from a to 0, plus, and the same thing's going to be over here, but I have the limit as b approaches infinity of arctan of x evaluated from 0 to b. All right, so if we start chunking in values here, we have the limit as a approaches negative infinity of arctan at 0. Well, arctan, or inverse tangent, at 0 minus inverse tangent at a, and then plus the limit as b approaches positive infinity of basically the same thing. We have the inverse tan of b minus inverse tan of 0. So keep in mind the inverse tangent is 0. That's saying tangent of what angle gave us 0, and tangent of 0 is 0. So that tells me for that portion there, this is going to go out to 0. And then here, minus the inverse tangent of A. In other words, tangent of what value makes us tend toward negative infinity, and that's going to be those pi over 2's. That's where you're getting 0 in the denominator. So notice for this one, that answer there is going to tend toward pi over 2. And then plus, and you're going to end up with the same thing over here. This value, as you're approaching infinity, you're going to end up with another pi over 2. And so notice you're going to end up with a value of pi, which is finite, and you can say this is convergent. Hey, here's another way that they could possibly ask these questions. Look at the first part. It wants you to sketch a graph of 1 over the square root of x minus 2. Now, I do know here if I let x be 2, notice what's going to happen here. Because we're looking from 0 to 5, but if we look at f at 2, notice what's going to happen. We have 1 over the square root of 2 minus 2, which is 1 over the square root of 0, or 1 over 0. So at 2, even though I'm looking for this area from 0 to 5, if I look at here at 2, what's going on is I have a vertical asymptote there. So I know that from 0 to 5, I've got some kind of discontinuity here, and my graph is going to be bending toward this direction here. I know it's going to be positive. And so here, why would we need to consider this improper? Well, we need to consider that improper because at x equals 2, then our function, we can call it f of x, has an infinite discontinuity or a vertical asymptote, either one you want to say. So I know that that is going to give us a problem. And notice how we're going to solve that integral in part B. We're going to let t represent that value. So what we need to do, it looks like this is just going to be a u sub. So we're going to let u be equal to all the gobbledygook under the radical. So du is dx. And so really this becomes the integral of 1 over u to the 1/2 du. And if I were to integrate that, let's see, that's going to be the integral of u to the negative 1/2 du. And so, can't see that negative there. So it looks like we're going to end up with 2 u to the 1/2. And then we do need to go back and replace that u with x minus 2. So that's going to be 2 times x minus 2 raised to the 1/2. And that's going to be evaluated from t to 5. And so here we're going to end up with 2 times, let's see, 5 minus 2, so the square root of 3 minus 2 times the square root of t minus 2. And so here, again, that's about as far as we can go. That's going to be our limit value, or not our area here. Okay, looking at part C. Now let's find that limit, and notice that we're only approaching from the right side, because on the left side we're not going to be able to find any values. There's nothing over there because I'm taking the square root of negatives, and that can't happen. So we found what s at t was. So now let's look at our limit. As t approaches 2 from the right, of 2 square root of 3 minus 2 square root of t minus 2. So if we're coming in from 2 on the right side, notice that this portion right here, if I think about plugging in values, notice if I let t be, this is 2 times the square root of 2.000, and we could go on forever, 1 minus 2, notice that whole value there is getting super duper close to 0. And so 2 times 0 is still 0. So it looks like that is just going to turn into 2 times the square root of 3. Okay, now we're going to look at our places where we might have discontinuities. And that's going to go along with the example we just looked at. So in example 6, this is a good classic example. Notice that we are looking at integrating the natural log of x, and that is going to go from 0 to 1. But if we look at the graph of the natural log of x, we are going to have something that looks like this, where you're getting super close to 0, but you're never ever going to cross that y-axis. So this portion here is going to be a point of discontinuity for us. So what we need to do when we set this up, we're still going to replace that. We're still going to do a limit, and we're going to call it a approaches 0, but we're going to keep to the right of it because there's nothing really there to the left for us to come in and see. So we have this, and then the integral from a to 1 of the natural log of x dx. And we'll again have to do our integration by parts. Over here to the side, we're going to let u be natural log x, and then du is going to be 1 over x dx, and dv is dx, so v is x. So putting this back together, we have the limit as a approaches 0 from the right of the integral of all of this. But notice we can do our sunshine minus voodoo, so sunshine, uv. So I have x times the natural log of x, or absolute value of x, let's keep that in there, minus the integral of v du, which is going to be x times 1 over x dx. All right, so let's continue on with the problem now. So we have the limit as a approaches 0 from the right of x times natural log of x, absolute value of x, minus, and of course those will cancel each other out, and if we integrate 1 dx, then we just get our x back. And now we're going to have to evaluate this from a to 1. So now let's see what that limit's going to look like. As a approaches 0 from the right, we're going to plug in a 1, and we have 1 times natural log of 1 is 0 minus 1. So there's our first part. And then we're going to have minus, and then we're going to have a times the natural log, absolute value of a, minus a. All right, so now notice what we're going to end up with, because again we're approaching a from the, or approaching 0 from the right side, so this stuff is getting smaller and smaller and smaller. So it looks like here that's going to be 0, so I have a negative 1 minus, and all of these things are getting super small. They're approaching 0 from the right side, so pretty safe to say that's going to hit out towards 0. So again we end up with negative 1. Okay, this problem very similar. Notice that we're looking over the interval from 0 to 3. However, if we have 1 plugged in, we're going to get 0 in the denominator again. So what we're going to have to do is divide this up around 1. So what we can do here when we divide this up, we're going to look at the integral from 0 to 1 of dx over x minus 1 plus the integral from 1 to 3 of dx over x minus 1. Now what we can do here now is come back and do our substitution at these endpoints. So we're going to say the limit as b approaches 1, but this is just going to be coming in from the left because I'm looking between 0 and 1, so that's to the left of 1, of the integral. And so I'm going to say from 0 to b of dx over x minus 1 plus, and we're going to do the same thing over here, but that limit is going to be from down here, we're going to say a approaches 1 from the right of the integral from a to 3, and that's times dx over x minus 1. And this is the case of where the derivative of the bottom is the top, so we have natural log. So we have the limit as b approaches 1 from the left of the natural log, the absolute value of x minus 1, and then that is evaluated from 0 to b, plus we have the limit as a approaches 1 from the right of, and again this is natural log, absolute value of x minus 1, and it is evaluated from a to 3. So plugging in here, we're going to have the limit as b approaches 1 from the left of the natural log of absolute value b minus 1. And then I've got a 0. If I plug in 0, I'm going to get 0, plus the limit as a approaches 1 from the right of, and if I plug in here, I'm going to have the natural log of 2 minus the natural log of absolute value of a minus 1. Well, notice what's happening here. If I'm looking at 1 coming in, let me change colors. So I'm looking at 1, I'm approaching 1 from the right, or from the left, so notice that is getting increasingly small, and if I look at my natural log function with that, this is actually approaching negative infinity here, as because that's getting here approaching 1 from the left, and that has been moved over 1, so you have something that kind of looks like that with our asymptote here. So you are tending toward negative infinity. And honestly, even though we finished out the problem, the moment you notice that one part of that is going to be divergent, then you can stop. This limit does not exist, and you have what's called a divergent case. You are divergent.